So again, I'm Anthony Hickey with Richard Sladen Associates. I'm a hydrogeologist, and I'm going to be talking about our portion of the hydrogeologic conceptual model, the geologic framework and principal aquifers. So just as an introduction, Santa Clarita was underwater, and geologists like to think about how things were in the far past. So this was millions of years ago. The black line you see on the figure here is kind of the boundary of, for lack of a better term, we'll call it a historic bay. And so the ocean was higher, the ground was lower. It's all relative. And all of this area from Ventura all the way out to Santa Clarita and a portion of the San Fernando Valley was covered in ocean. And so a lot of the rocks we're going to talk about today, the geologic formations, are influenced and formed in this marine environment. And then over time, as we'll talk about, we all know about faulting and folding in California and ground uplifts, and those patches of land that were underwater come out of the ocean, and more geology is formed. So it kind of drives this whole area. So I really like this picture kind of showing, remember where we came from. This Santa Clarita was once underwater and then uplifted. So just some basic definitions. These are a lot of terms that I'm going to use repeatedly during this talk, and you're going to read repeatedly throughout these tech memos as part of the sustainability plan. And so just wanted to state the obvious and go through these in case you're not familiar. We have groundwater, and that's water beneath the Earth's surface. Surface water, that's water flowing in the rivers, streams, tributaries, all of those things that we see in the groundwater basin. Hydrogeology, Jeff already handled that, but it's the study of groundwater and surface water and how those two exist in a groundwater basin and move through the rocks in geology. I'm going to use the word formation a lot. And so the word formation, for the purposes of this discussion, the formation it's a group of rocks, a group of sediments identifiable over distance. So that means geologists have done a lot of work and a lot of study, and we feel confident that the rocks we see out there in that mountain are the same as those, and they were formed at the same time. And that's a really important concept. We're going to talk about the Saugus Formation and the Pico Formation during this talk. And so it's just a group of sediments. There are clear definitions at the top and bottom of those sediments, those rocks that we're talking about, but it doesn't necessarily mean they're drastically different. It's an identifiable package, so we feel confident we can call those things across distances. And that's how we help define some of these things in the subsurface. I'm going to talk about aquifers. And, just one important thing about an aquifer, a lot of times when people talk about aquifers, they like to think of underground lakes or underground streams. Maybe they imagine it in a huge tunnel or a big open area filled with water, and that's not what an aquifer is. An aquifer is a group of rocks or sediments that can store water, and the way I like to think about it at its simplest is a bucket of sand you collect at the beach. If you filled up that bucket with sand and dumped water in the top, the water is going to go in there and you're not going to see it anymore. That's an aquifer. And so the water moves through all those little spaces in between those sand grains resting against each other. So when we talk about an aquifer, that's what we're talking about today. We're talking about the groundwater basin and the sustainability of this groundwater basin. It's a definable contained area with one or more aquifers. This is simplistic. I'm sure some attorneys would argue with this definition, but just for the conceptual wise, it's a contained area that we can say this is the groundwater basin, and there's not necessarily influence from inside or outside. That's not entirely true, but for today we'll say it is. There's the hydrogeologic conceptual model, which Jeff did a great job talking about, and I just want to reiterate it to make sure it's clear. When we talk about hydrogeologic conceptual model during my presentation, we're talking about a conceptual idea. I'm not talking about a computer model. I'm not talking about a some kind of computerized image where we're calculating how much water. We're just talking about a conceptual idea in our heads. What does the basin look like? What rocks make up the basin? And how does water move through the basin, in and out? And to help us visualize some of those subsurface structures, shapes, etc., that Jeff was referring to, we're going to create cross sections. And that's how hydrogeologists try to represent that 3D shape on a flat piece of paper. And I really like to talk about this as a layer cake. Imagine the groundwater basin as a layer cake. And when we're looking on Google Earth, looking down at our groundwater basin, we're looking at the top. And a cross section is putting a knife through, taking a slice, pulling that away, and looking at the layers under the ground. So I'm sure there's more definitions that are needed. Feel free to ask, but those are some of the basic ones I'm going to use today. So to start off, we're going to talk about the basin boundaries. How is the basin defined? The purpose of all of this is to get a sustainability plan for this basin. So let's talk about what makes up the basin. The purple line shown on the screen here is the groundwater basin boundary as defined by the Department of Water Resources, DWR. Our basin number is 4-4.07, and we're the Santa Clara River Valley Groundwater Basin, the East Subbasin. So these groundwater basins are essentially, we are the easternmost of a series of basins, follow the Santa Clara River toward the ocean. But for our purposes today, we are talking about this purple area, and this is the basin that the groundwater sustainability plan is being prepared for. This purple boundary is based on geology. And that's going to be the theme today. I'm a hydrogeologist, so I'm going to show you why that purple boundary is where it is. We've labeled some key areas here, Bouquet Junction, New Hall, some of the canyons there, and then the Santa Clara River running through the middle, and here's your freeways just to get you some bearings. And we are connected to the subbasin to the west. We'll talk about outflow out of our groundwater basin later. So again, our basin is based on geology, and I'm presenting this now. We're going to lead to this eventually. This is kind of the punchline, but we've got an orange aquifer, the alluvial aquifer, the Saugus Formation aquifer in green, and the purple boundary. And so that purple line surrounds the both of them. So let's talk about how we get there. Sorry, I would like to mention one more thing. In a lot of these slides, you'll see something that says Tech Memo Figure 1.4. So if you wanted to go back to the Tech Memo that's been produced, that's the figure number in the Tech Memo. They're not exactly the same. I've changed the colors and made some of the lines thicker to make it match, but this base map here you see in the background is Tech Memo Figure 1-4. So the basin is defined by geology. What rocks make up our groundwater basin? So in the center here is what geologists call a strat column. This is the stack of rocks in the groundwater basin. To the right of the slide, we see a simplified cross-section, a simplified stratigraphic section to show the relationship of these different rock types down through the groundwater basin. So this figure here shows a number of things. One, it shows the relative thicknesses. The alluvium is relatively thin on the top of the groundwater basin here. We have the Saugus Formation, very thick through the middle, and then the Pico Formation down at the bottom. Now, the Pico Formation is lopped off in this case. I'm not showing the full thickness because, as we'll get to, the Pico Formation we'll call the bottom of the basin. The alluvium is relatively young, about 10,000 years old at its oldest. The Saugus Formation is 1.8 to 3.6, and as I mentioned, that the basin was uplifted over time, and so this Saugus Formation was being formed before, during, and after the uplift of this basin. So some of the Saugus Formation was formed when things were above the ocean, maybe the upper portion and some of the lower portion here, and then the lower portions may have been formed when the land was mostly covered with the ocean, and so that results in geology that it affects the grain size, and those formational environments, how the rocks were formed, affects how groundwater exists and moves through those materials. We divide the Saugus into not two formations, excuse me. We divide the Saugus Formation into what we call two different members, but you'll see throughout the Tech Memo, there's the upper Saugus portion of the Saugus Formation and the Sunshine Ranch portion. In general, the Sunshine Ranch portion is made of smaller particles and maybe a little more compact than the upper portion. So where can you see these things? Looking at the alluvium, again, it's relatively young. Jeff mentioned earlier, the alluvium, these are sediments that are transported by the water. So you're going to find these sediments in the tributaries in the bottom of the Santa Clara River and all of those streams that flow into the Santa Clara River. You see a different mentions of thicknesses. In general, if somebody asks you how thick the alluvium is, you say it's about 100 feet. Some areas it's actually 200 feet, some it's a lot thinner. But that's the rough range of thicknesses for the alluvium in the basin. And we got a picture here along Soledad Canyon Road looking out into the river. And so this is something that you might see driving around the groundwater basin. There's the alluvium in plain sight. You can go touch it and experience it. The Saugus Formation. So this is a beautiful outcrop of Saugus Formation you can see on the 5 freeway. This is on the east side of the 5, just before the Calgrove exit. As I mentioned previously, it's formed from shallow marine, which means under the ocean, and then some of it was formed out of the ocean. We got big boulders, we got big rocks in there, we got smaller gravels, and then we have sand and silt. So a lot of different grain sizes, and you see these wonderful bands. You also might ask why these bands are tilted. Was somebody standing to the side when they took this picture? No, this is natural. This tilting is caused by all of those processes we talked about, faulting and folding, that we know about in California, and Jeff alluded to that bowl shape. And so this is one of those spots where you can see the Saugus Formation in its tilted angle and start imagining how it could form a bowl shape underneath the ground in the center of the groundwater basin. The Saugus Formation is primarily for municipal supply, but we'll get to those, the breakdown of how the groundwater in each of the basins is used in a moment. There it goes. Here we've got the Pico Formation on the screen. So this is an older formation, 6 million to 3 million years old. And this is, we have on here made up primarily of claystone. So claystone is even smaller than sand and silt. So the point of that is the particles are very, very small. For the purposes that we're discussing today, this is considered to be non-water bearing. We don't assume that the Pico Formation could provide you any water if you constructed a well. There's exceptions to every rule, but for the purposes of the definition of this groundwater basin, the Pico Formation is non-water bearing. And this was earlier in that process when the Santa Clarita Valley was underwater in that bay that I showed you at the beginning. This was formed in a deep marine environment, and that's why we get those real small particles. It's very compact, and water doesn't move very easily through these rocks. And this underlies the Saugus Formation. So this photo you see here is on the north side of the 14, just east of the interchange with the 5. Sorry, we're missing a number there on the slide. And this is also tilted due to folding. And so again, you get to see some of that bowl shape and understand that, you know, if you imagine those tilted beds going deep into the ground, how you might form a bowl underneath the groundwater basin here. So then we mentioned faults and folds, and we all live in California. We've all felt an earthquake, I'm sure. And so these are the places on the ground where sometimes you get breaks, sometimes you don't, where formations move past each other. And this is very important to the formation of the basin. We talked about that uplift, and as a part of as a function of all that movement, you get these faults and folds, which are boundaries. They can be boundaries between formations. They can be a spot where the movement occurred, and then associated with that, the ground moves and folds around it. And so this is a screenshot here from Google Earth on the right, and this is where the San Gabriel Fault, the trace of the San Gabriel Fault is mapped to cross the 14 freeway. And you can see some evidence there, but if you look a little closer, and I'll just jump back and forth if the internet will allow me, you can see those red lines bounce. And so if you look at that, you can see some of those beds being bent and folded. Faults, on maps, we like to put a nice straight line, as you'll see in my next slide, showing where the faults are. But in reality, faults are a little more complex. Typically talk about them as fault zones. They can be one perfect straight line, but they can also have smaller faults, and maybe it's not continuous and the line jumps over here. So when we show a fault on the map as a big, long, solid line, remember that it can jump around, and that's approximate. And I just think this is a really nice picture where you can see, along with the faulting, you get some of those folds, maybe some smaller faults nearby with those straight lines I'm showing there. And so when you get faulting in an area, you can really move things around, and that helps define what the shape of this basin looks like. So here's a map of the groundwater basin with those faults, and these are the two most important faults, I guess, with respect to the groundwater basin formation and groundwater occurrence, the San Gabriel Fault and the Holzer Fault. And so these two faults intersect at Bouquet Junction there, where you see in the center, and they connect, you can say, here. And so it's very important with respect to the Saugus Aquifer, this relationship between these two faults and how they move through the groundwater basin. What's important is faults, when they move and they move formations, if that formation is one of the principal aquifers in the groundwater basin, you can segment the aquifer and make different areas that maybe act a little different with respect to recharge and pumping, and maybe they communicate, or maybe that communication, water movement between them is diminished. And it's a really important part of this, and it helps define the Saugus Formation aquifers, like we'll talk about in a second. So we've talked about the geologic formations. We've talked about some of the structure, the faulting and folding that occurs and how that affects those formations. And so I mentioned cross sections. What we've been focusing on, the maps I'm showing you, is looking at that map from top view. We're looking at the cake from the top down. So now we as hydrogeologists want to draw these cross sections and show what it looks like under the ground. What is the shape of the basin? So the way we do that, again, is with these cross sections. Highlighted in gray on the screen are 5 cross sections that Richard Slade & Associates created for this GSP. Tech Memo 1.4 there, and we'll get to the sections in a second. But again, these are created to help illustrate the relationships of geologic formations. What's on top of what? How thick is the Saugus Formation on the east end? How thick is it in the center? Where does the alluvium actually touch the Saugus and where does it not, etc. All of those are important. If we're going to talk about sustainability, we need to understand how the water can move through these formations and how it interacts with each other in the subsurface. So how do we create these cross sections? So the interpretation of the superficial geologic map, again, been showing Tech Memo figure 1.4, we're looking down. Then when people drill water wells, and there's a lot of water wells in the Santa Clarita Valley, a lot of times, or most of the time, or hopefully all the time, a geologist is on site looking at the actual materials that are coming out of the well, out of the drill rig. So you got your drill rig going, and all that material you're getting rid of is coming out to ground surface, and someone like me, a hydrogeologist, is there to look at those, describe them, and that helps us understand, are we drilling through alluvium? Are we drilling through the Saugus Formation? Have we already hit the Pico Formation? So that's one really key piece of data. Another key piece of data is what we call geophysical electric logs, and we throw this around as E-logs. And the way we like to describe those, it's a borehole fingerprint. And so you take this device, you put it down this hole that you've drilled in the ground, and it makes some electrical measurements, and you get this fingerprint. And each of those fingerprints are shown here on the screen with these squiggly lines. They've been color-coded for various reasons on this figure. But we get these from oil wells, and there's a lot of oil production, or historic oil production in the area, and importantly, what we call wildcat oil wells. When historically people were looking for oil, they would drill a hole in the ground to a great depth, and they hoped to find oil. Luckily, even if they didn't find oil, they typically did one of these E-logs. And so it's very important in the oil industry, and we can use those to help define the groundwater basin. Anytime the water districts drill deep wells, some of the larger ag wells, and even the alluvial wells by private parties, these E-logs are very useful. So we take those E-logs and we put them on a map, and to make it very simple, we try to play connect the dots. And what does that mean? We've got these E-logs here, and depending on sand, water occurrence, etc., these squiggles react differently. And so what we try to do is say, this squiggle and this squiggle, we think they're the same. And I'm making it sound very simplistic. It's obviously more than that, but we use the geologic subsurface information, we use our location, we use that surface mapping, we use this fingerprint and say, can we connect these dots? So the way that we go about doing this is these dashed brown lines is where we said, based on all the data we have, those look like they are the same aquifer in the same formation, or those are related and deposited at roughly the same time. So for all intents and purposes, we are the same. If we connect enough of those dots and we have enough of that information, we can start following where those beds go. Here, that bed is at 50, here it's at 100, here's at 150. And so we can start defining those shapes that explain the groundwater basin. So after we've done all that work, what we end up with are these hydrogeologic cross sections. I got two examples here. These are two of them. They're very difficult to see at this scale. I understand that. Tech Memo figure 1.6 and 1.9. But what's important is this bowl shape. And so you see, after we've done all our work, all of these black stripes are wildcat oil wells. These blue and red stripes are either municipal production wells or private wells or irrigation wells or monitoring wells that may have had e-logs or geologic logs. We use that geologic information. And so what you see here is a few things. Number one, you see that a lot of these deeper wells are constructed into the upper Saugus. So that's a key formation. You also see the Sunshine Ranch formation here, which does define the bottom of the basin, but there's not a whole lot of wells constructed into that Sunshine Ranch formation. You've got the Pico formation underlying that, which we've talked about non-water bearing, which I'll show in a second. And relatively speaking, thickness-wise, that alluvial aquifer is thinner compared to the Saugus. Again, there's 5 of these in the Tech Memo, and they're in PDF, and you can zoom in and out and see them a little bit better. There it goes. So we've talked about defining it with respect to the geology and the subsurface information we could find. And now we need to talk about the principal aquifers. This is a groundwater sustainability plan. And so where is the actual groundwater? So as Jeff mentioned, there's 2 principal aquifers that make up the basin. We're going to talk about the alluvial aquifer and the Saugus aquifer. And I just cut out these shapes. I think it's interesting, and you know, this shape will appear on the following slides. The alluvial aquifer follows those canyons that lead into the Santa Clara River, as we discussed, and the Saugus aquifer down under the ground is more of that bowl shape and a little more massive. So we'll see these 2 shapes pop up on the following slides. So there's the alluvial aquifer again. We saw this earlier. We've got our strat column here reminding you that the alluvium is just a thin line up at the top, relatively speaking, thickness-wise. And you'll notice that, you know, it's an obvious thing to state, but this alluvium is deposited by the river, but that Santa Clara River is right in the center of all this alluvium. And all of these canyons, Mint Canyon, Sand Canyon, Bouquet, they all lead down to the Santa Clara River, and that Santa Clara River flows out this way. So this alluvial aquifer is where that surface water and groundwater interact. And I know that Andrew from Ludorf and Scalmanini will talk a little bit more about that, and later Tech Memos will deal with that more. But the alluvial aquifer is important in that that's where that interaction between surface water and groundwater occurs. So some facts about the alluvial aquifer. Remember I said previously it's roughly 100 feet deep. The max depth is probably 200 feet there in the center. This is that block diagram Jeff showed you earlier. Really nice diagram that just kind of captures all of the ways water moves in and out of the groundwater basin and the 2 aquifers, the alluvial aquifer and the Saugus formation. So we'll just drill through those. The alluvial aquifer, when you talk about groundwater flow, how does groundwater move through the aquifer? And we have a lot of terms in the Tech Memo to talk about how that happens. We have a lot of ways of defining that. We do pumping tests with wells and other things. But the key here is that in the alluvial aquifer, groundwater moves faster relatively than the Saugus formation. So there's more open space, it's less compact, and water can move easier through the alluvium than the Saugus formation, generally speaking. And so the alluvial aquifer is a groundwater source. As you see on the block diagram here, there's a lot of different sources. And so there's environmental needs because the groundwater, in some cases, as I just mentioned, can become surface water flow. So that's important for environmental needs. Plants can use the groundwater. We'll talk about that in a second. There's industrial supply wells. There's agriculture and irrigation wells, there's private domestic wells, there's municipal supply wells. So all of these sources, all of these uses derive water from the alluvium. So it's one of the key important aquifers in the basin. Now let's talk about the Saugus Formation aquifer. There's our green block again. And so we saw our massive green area, that's all Saugus Formation, but I've got the fault laid on here now, our simplified big long fault. And it's important because those faults, the San Gabriel Fault and the Holzer Fault, split the Saugus Formation into three aquifer areas, let's call them. We call it the North Block, the South Block, and the Central Block. And because of the faulting and because of the movement and the folding we've talked about, the thicknesses of the Saugus Formation are different in these areas. Central Block is a little thicker than the South Block. The Central Block and the South Block have more of the upper Saugus, that's a little more water-bearing. And the North Block, generally speaking, it's not 100% true, but the North Block is made up a lot of that deeper part of the Saugus Formation here that we talked about, the Sunshine Ranch member. And remember I said the Sunshine Ranch, smaller particles, doesn't have as much room for groundwater storage or movement. So in general, Saugus Formation wells in the North Block are not very productive, and we'll probably not see a large municipal well constructed in the Saugus Formation in the North Block because of that. The South Block and Central Block are where most of those exist now. So that fault, those faults cutting through are very important where we talk about that. And this is important for part of the sustainability. Others will talk later. Andrew from Blue River Scamanini will talk a little bit about an introduction on groundwater storage. And so looking at these different blocks is a key piece to that. So the Saugus aquifer, it's a deep aquifer, and you've got that on this block diagram here. You see these very deep Saugus wells. So water is known to be available at about 2,700 feet or more. And that's kind of a practical limit. There's some other factors that go into it, but to get water from that deep, you have to drill a hole that deep and put steel in the ground and create a well. So there's some practical limits to how deep you can go. It doesn't necessarily mean there's not groundwater below there, but that's where we talk about the, sometimes we call it the producing area, the producing depth of the basin. But there's a lot of nuance to that comment that we won't go into right now. It's key that it exists beneath the alluvium in most areas of the basin. So remember our picture that I'm going to allude to again with the purple line. And that alluvium sits on top of the Saugus aquifer. And that's important to understand how groundwater relates to those two and might move between the alluvial aquifer and the Saugus aquifer. Forms a bowl in the basin, and there's a nice picture on this conceptual diagram here of what that bowl might look like. And we talked about the relative formations there. And again, in the Saugus Formation, because of its many factors, how compressed it is and the grain sizes, the size of the particles that make it up, groundwater moves relatively slower than it does through the alluvial aquifer. And groundwater from the Saugus Formation, it's primarily municipal supply. Historically, there may have been an ag well in the Saugus Formation. We don't think that's producing anymore. So the Saugus Formation, for the purposes of today, should just be considered as a municipal supply source right now. That and some groundwater can move into the alluvium, which we'll talk about now. So just wanted to bring it all back to this again, how we started the basin boundary. How do we define it? We define it with geology. If you take that alluvial aquifer and you lay it on top of that Saugus aquifer and draw an outline around the two, that's how we get our basin boundary. Also, I like this figure because it shows that on this end here on the east, the alluvium does not overlie the Saugus. The Saugus extends only to about here. And so there's a little portion of the alluvial aquifer that's not on top of the Saugus, but for the most part, the alluvium overlies the Saugus Formation. Outside of the basin boundaries, we've got this older Pico Formation, and we call it non-water bearing. I've got this dashed line here. That is not to say that everywhere you see this dashed line, you could walk and see the Pico Formation at ground surface. This is just a limit of it at underground. In actuality, the non-water bearing formations, there's a lot of other formations, Tit Canyon, Mint Canyon, the Violin Breccia, volcanics, that make up these non-water bearing formations. But the way we think about the basin is outside of the purple line, non-water bearing. Beneath the Saugus Formation, non-water bearing. and everything inside the purple line, water bearing. So finally, we've talked about what the hydrogeologic conceptual model is related to the shape, where the water is, how the aquifers are formed and exist, and now the final point of this portion of the talk is the groundwater recharge and discharge areas. How does water get into the basin and the aquifers, and how does it get out? And we've touched on a few of these before, but these slides will summarize those ways. And again, this block model that Jeff introduced earlier, it's a really good summary of the ins and outs of the basin, and that's it's a really nice way to show it. And so we have inflow from upstream areas along the river. Remember that river flows across the alluvium, so that's one way water can get into the alluvium. And this is recharge. This slide focuses on ways water gets into the alluvium. So it's via the river. Deep percolation of rainfall, when it rains and it hits the ground surface, it has a chance to make it down to the water table in the aquifer. There's those discharges of water reclamation plants and treatment plants that Jeff was mentioning. When those get discharged out into the alluvium, that water has a chance to make it down into the aquifer. There's the irrigation return flows. So we water lawns, we water golf courses, if there's a farm or agricultural operation, when water's applied, the water starts moving downwards, and the plants take some, and some of it evaporates, and sometimes there's leftover and it makes it down. And so that does occur here, and that is another way that recharge occurs in the groundwater basin. And then we'll visit this one or two times, but this upward groundwater flow from certain portions of the Saugus Formation. So generally, we're going to talk about it in relation to Bouquet Junction, which I guess is roughly here on this drawing. But on the western end of Bouquet Junction, there's some spots where the Saugus Formation is in connection with the alluvial aquifer, one of those spots where they overlie from our purple boundary picture. And the water in the Saugus Formation, naturally flowing, flows out of the Saugus Formation and into the alluvium. So that's one way recharge occurs into the alluvium. Recharge into the Saugus aquifer, not as many green boxes here, but we've got infiltration from alluvium. So just like we talked about water moving out of the Saugus Formation here west of Bouquet Junction, east of Bouquet Junction, water can move from the alluvium into the Saugus. And so that's one method of recharge for the Saugus Formation. There's also the deep percolation of rainfall, where it rains directly on the Saugus Formation. That can deep percolate into the water table. And then we've got the irrigation return flows. It's not as common, but where there is lawns or agriculture or a golf course and the plants don't take it up and it doesn't evaporate, that can move down into the groundwater. So those were ways water moves in. Now let's talk about ways water moves out. And so we've got discharge from the alluvial aquifer. Subsurface outflow that Jeff mentioned. In the subsurface, not even talking about the surface, there can be water that moves out of the basin that way. There's those plants we talked about. The word is phreatophytes, but they've got roots in the water table, and those are very effective groundwater pumps, and certain plants can remove quite a bit of water. So that's one way water is removed from the basin. There's the surface flow. We know that the Santa Clara River at times and in some areas flows, and it can go out of the basin. And that discharge is called base flow. That's a little more focus of Andrew from Ludorf and Scalmanini's presentation next, but that's one of the concepts is water can leave the alluvium and become surface water flow and leave the basin. And then again, we talked about the inflow into the Saugus and of course pumping extraction. There's a lot of wells in the alluvial aquifer. We talked about those possible uses, and that's a direct removal of groundwater from the alluvial aquifer. And then discharge areas from the Saugus aquifer. Again, the pumping extraction, we know that the Saugus is important for municipal wells. And there's that upward groundwater flow west of Bouquet Canyon where water can move into the alluvium. So a nice simplified view again with that block model of where the water moves in and out, how groundwater might become surface water and leave the basin or leave by other means. So again, just to summarize, the purpose of this hydrogeologic conceptual model is just to gain a conceptual understanding of the shape, how water moves through the basin, because if we're going to talk about sustainability, we need to understand where it is, how much is there, and how it moves through the basin. So with that, I'll turn it back. Tara, questions, or you're going to facilitate that?
I'm so muted. All right, so I'll be facilitating the question and answer period. I've recorded all the questions that we've asked through chat, and once we get through those, then we'll have people raise their hands. So first, what does Sunshine Ranch member mean? And Heather, did you get this question answered? Because I know he kind of went into it a little bit more, or did you want more of an understanding than what he provided? Heather?
Yeah, I think I've got it. So it was the different grain sizes of the bed. That's kind of what the difference is, and you're a member, I guess, if you have the right grain size rather than the right card, I guess. Is that kind of the gig?
Yeah, that's a good way to put it. So a member can be a portion of that overall formation. So it's all the Sunshine Ranch. We think they're related, but as I mentioned, things were changing geologically when that was being formed, and so the Sunshine Ranch member is a finer grained materials that aren't as good at storing or allowing us to get at the groundwater.
Okay, and then the next question, by the way, thank you, Maria and Jay Isaacson, for your comments. The next question is, what is the relationship between the aquifers and oil deposits in SCV? Now, Dan says that there's no relationship. The oil reservoirs are typically much deeper than the water-bearing aquifers, but I want to make sure that we're all running to the right channel. So could you answer that for us?
Yep, I completely agree with that. The oil-bearing materials are much, much deeper than the water-bearing materials. Simplest way to look at it.
Fantastic. And then Steve Sly asked, why does the State Water Resources Control Board differentiate groundwater and alluvial water? And here they are called one and the same. The state clearly considers groundwater to be below the alluvium. So if you could explain that kind of separation / merging.
Yeah. That is one of those questions that we could probably talk about for a long time. The definition that the state has for groundwater versus surface water. I know there's some attorneys on the phone who probably have some very specific opinions about this. But that being said, they're interconnected, and I think that's one of the purposes of the discussion today and talking about the interconnection between the two is that groundwater can become surface water and vice versa. Do you think that's fair, Jeff?
Yeah, can you hear me?
Yeah, we
Yes.
can.
Okay, great. Yeah, here I am. So within the alluvial aquifer that is connected to the surface water body, if it has defined beds and banks in the subsurface, it's considered underflow and is treated the same as surface water from the State Water Resources Control Board point of view. Groundwater that occurs outside of the bed and banks is considered percolating groundwater, which frankly, don't ask me to explain that differentiation because it is a legal discussion. But, it's all groundwater from our point of view, the hydrogeologist point of view, but from a legal lawyer point of view, water rights point of view, there is a distinction there.
And my understanding is that there's going to be an entire workshop on the surface water, groundwater integration thing, right?
Yes, there is, but we're not going to get into differentiating water rights from the State Water Resources Control Board point of view. Happy to describe it with regard to our understanding of bed and banks and the alluvial aquifer and what it means, what is considered underflow related to surface water versus what is not.
And so just tying on to that, Maria wanted to ask, so do we have some alluvium outside the bed and banks?
Well, okay, so it depends on which surface water body we're talking about. So along the main channel of the Santa Clara River is clearly, there's a defined bed and banks there. There are tributaries to the Santa Clara River where I think that can be debatable, whether there are defined bed and banks to that. But I'd have to say there's a legal argument to be made there
Great.
for alluvium that's outside of the main channel.
And since we're not going to do the lawyer thing in this moment in time, let's move on to Dina's question. Does slower groundwater movement in the Saugus Aquifer mean slower recharge rate? Now, Dan has answered yes, but I thought maybe we might expand upon that a little bit.
Yeah, that's fair. It's probably a little more complex than that. Once, water moving through what we call the vadose zone, the dry part of the soil, getting down to the aquifer is one thing, and then that water moving through the aquifer to another place is another. But in general, yeah, I think that would be a fair statement.
Great. And then Lynn's question is, where is the ag well in the Saugus that is not producing any longer?
Somebody might have to jump in and
that.
Thank you.
Yeah. Well, the one Saugus well that I know about on Newhall Land and Farming Company's property is in Middle Canyon. That's no longer used. That's just kind of south of Magic Mountain, around the bend, in the southern western portion of the basin. I think there are other Saugus wells that have been used for irrigation, and I don't know exactly where those are.
Great. And then Kathy has a question. What are ways that suburban environments like ours can improve infiltration of rainwater for groundwater recharge, removal of concrete where appropriate, use of more permeable surfaces? What are some ideas on that?
So those are generally some of the ways people are looking at. There's, we talk about the low impact development rules that have come about in a lot of different municipalities and counties. And so the purpose of those is to keep dirty water out of the river, but there is a side benefit that the opportunity for deep percolation of groundwater is increased. So those are some ways that are typically talked about as ways to increase groundwater recharge. There's other ways, and Jeff, if we're going to talk about these. I think they're mentioned briefly in the tech memo that there may be people looking at, some ideas looking at artificial recharge, where you can put a lot of water at ground surface to help it get in a little more, or you can inject it with a well. There's a lot of different ways to help increase the amount of water that gets into the ground.
That's right. We're talking about SCV Water is investigating, diversion of storm flows for recharge, slowing the water down before it leaves the basin, recharging with State Water Project water, other treated water, or injection of water, treated water directly into the Saugus Formation is another concept.
And with that, are there any more questions before we move on to our second presentation? I do not see any hands raised, and I do not see any more questions in chat. Oh, one more question from Sandra Cattell. Is percolation diminished by encroachment into the floodway and floodplain?
I could take a shot at that.
Yeah, yeah.
Well, when we talk, I guess it depends on what we mean by encroachment. If there's impervious surfaces that are extending into the floodway or the floodplain, obviously that can limit infiltration or enhance stormwater runoff. So I think the question is, how prevalent is that? Is that certainly historically we've seen a lot of encroachment, but I'm not sure that we see it anymore unless there's some examples people know about.
Okay, and any more hands raised or questions before we move on to the next presentation? We'll have another Q&A session. All right, seems like thank you so much, Tony and Jeff. We'll move on to Andrew. Oh, he's in the corporate boardroom. That's exciting.
Yeah, I came into the office today. We're starting to open up here in Sacramento. So, all right.
But a lot of social distance. I like it.
Yeah, in the office, by myself here. So, all right. So today, I'm going to be presenting the groundwater and surface water conditions portion of the hydrogeologic conceptual model. And the goal of my presentation is to present an overview of what current and historic groundwater conditions look like in the aquifers that Anthony has just described, the two principal aquifers being the alluvial and the Saugus Formation. So how we're going to identify groundwater conditions and discuss them and how they've changed over time, if we can get the slide to change here. Here we go. So we're going to look at the 6 different sustainability indicators that have been outlined by Sigma. And these sustainability indicators are the different elements or components of groundwater that allow us to quantify and understand what an aquifer is doing in relation to management practices or climate. And those include interconnected surface water, groundwater, groundwater elevation, and we're going to look at that in 2 ways. We're going to look at groundwater elevation contours, but also hydrographs. We're going to discuss change in groundwater storage, seawater intrusion, subsidence, and finally, groundwater quality. So our first topic is interconnected surface water and groundwater. And today we're not going to discuss in detail or go over any data from the East Subbasin for interconnected surface water groundwaters, but we're going to provide an overview of what this is. And an interconnected surface water groundwater is an area where you have a direct connection between the surface water body and the underlying aquifer. There's the area between them is completely saturated with groundwater. The pore spaces are completely filled. This is a requirement of Sigma, and we're going to discuss in an upcoming workshop the importance of interconnected surface waters, review some data and identify them throughout the basin, and discuss some related elements of interconnected surface water, which include things such as groundwater-dependent ecosystems. So one example of an interconnected surface water groundwater system would be a gaining stream. And in this diagram, you can see that the surface water, the stream here, is in contact with the aquifer. And by gaining stream, we mean that the aquifer is discharging to the surface water body. And the reason this is an example of an interconnected surface water, because you can see at the base of the stream, it's in contact with the water table. There's no zone of, there's no unsaturated zone between the water table and the aquifer. And under these conditions, the amount of discharge you see from the aquifer to the surface water body is going to vary. It's going to depend on groundwater conditions, what's the elevation of the water table, but also what's the elevation of the stream, what's the level that the stream is flowing at. Our next example is also an interconnected surface water system, but this would be an example of a losing stream. And this is where a surface water system or a surface water body is discharging or recharging the aquifer. We have water flowing from the surface to the groundwater. And under these conditions, the recharge is going to vary depending on surface water conditions and groundwater elevations. And our last example is a disconnected stream. This would not qualify as interconnected surface water groundwater because there's no direct connection between the surface water body and the underlying aquifer. And because they're disconnected, there's going to be no variation in the recharges being provided to the aquifer by the surface water system. So again, this is just a quick overview, and this will be discussed later in an upcoming workshop. Related to this topic of interconnected surface waters, Sigma requires us to identify the surface water bodies that are significant to the management of the basin. And in this figure here, we have all the naturally occurring surface water features such as the Santa Clara River and Bouquet Creek, but along with the reservoirs in the basin that provide surface water. And also we have the primary tributaries. These are the areas that drain to the main part of the basin. They feed the Santa Clara River. These are also important to point out because we use these to distinguish conditions in the alluvial aquifer across the basin. So we'll look at how conditions may vary in Cascade Valley versus how they vary in the, or how they look in the South Fork Another part of SIGMA is looking at your imported surface water supply. So this isn't directly related to groundwater conditions, but it looks at what is the available water the basin has. Santa Clarita has received surface water supplies from the State Water Project going back to 1980, and its intent was to provide a supplemental supply of water to the basin. And going back to when surface water supplies were first available, there have been an average of 26,000 acre feet of water per year. And in recent years, that's been as high as 40,000 acre feet due to wet conditions across the rest of the state. And in our figure here, we show the distribution system for the State Water Project or throughout the basin. And this is the main distribution line. And these little dots represent turnout points. They're the points at which water is taken from the main distribution pipe and sent across the different water divisions that are part of the Santa Clarita Valley Water Agency, which include LA County District 36, Newhall Water Division, Santa Clarita Water Division, and Valencia Water Division. Okay, so next we have groundwater elevation. And this is one of the required elements of SIGMA. We need to characterize what does groundwater elevations look like across the subbasin. So in this diagram right here, I'm trying to illustrate what is groundwater elevation and how do we measure it. So in this here, I have a generic example of how we would measure the depth to water. So we have sea level, which I should point out that when we talk about groundwater elevation, we measure it relative to sea level. So in my diagram here, I show how we indicate what is groundwater elevation relative to sea level. So in this example, sea level is 0 feet above mean sea level. And then this little brown line is representing bedrock. And this gray surface is going to be, let's say that's the east subbasin that makes up the alluvial aquifer and the Saugus aquifer. And we know at some point the ground surface elevation is 1,100 feet above mean sea level. So to get a groundwater elevation measurement, we take a depth to water measurement at a well, and we take that from the ground surface. So if we know the groundwater depth is 100 feet from ground surface, we know that the groundwater elevation at a given point is 1,000 feet above sea level. And the reason we want to look at groundwater elevation instead of depth to water is that if you are trying to compare groundwater elevations or groundwater levels across an area, you'll want to know how they compare. And if you have significant differences in topography and your land surface elevation, a depth of water of 10 feet in one area could be significantly different than an area that's 1,000 feet higher. So we need to look at it in terms of elevation to tell us which direction groundwater is flowing. So with that groundwater elevation data, we're going to look at two things. We're going to look at the groundwater elevation contours we developed, which are a snapshot of conditions, and they are intended to show the direction of groundwater flow. The SIGMA regulations require that we present contours for a current water year. And what that means is we show groundwater elevation contours for the most current year that data was available. And at the time these contours were developed, that was 2018. So I'll show contour maps for both principal aquifers, the alluvial and the Saugus, for 2018. And then after we look at those contours, we're going to look at the hydrographs. Hydrographs are a little bit different than contours. They don't show a basin-wide picture. They are measurements at an individual well, and they show the changing groundwater elevation over time. So with this, we can see any short-term or long-term trends that could be a function of things such as climate, groundwater extraction, or groundwater recharge over a wet period. And the reason this is important is that it informs how much water is available in the basin. So a little bit on how we create these contour maps. We're looking at contour maps for both the seasonal high and seasonal low conditions. And the seasonal high conditions occur in the late winter to early spring. And in this graph here, I'm showing the precipitation amounts for 2018. And the seasonal high conditions correspond with the times of the year that we see the greatest amount of precipitation. And that's typically between January and April. And in 2018, the greatest amount of precipitation occurred in January and March. And we'll look at the seasonal low contours, which occur towards the late summer, early fall, after extended dry periods throughout the summer, times that you're likely to have increased groundwater extraction. So with this seasonal high and seasonal low data, we'll create these contours by looking at the measurements at individual wells and interpolating between them to create equal lines of elevation. And you'll see those in my upcoming slides. So a little bit on the data that we use for the alluvial aquifer. So for the seasonal high conditions, we look at the depth to water measurements in a well. And those vary between 10 and 150 feet for the seasonal high conditions. And then under the seasonal low conditions, those same measurements vary between 12 and 150 feet. So those are they kind of cap off the measurements that we see in the alluvial aquifer, but you could see more variation between those values at a given well. So what these depths to water measurements translate into are groundwater elevation above mean sea level, results in elevations between 878 feet above sea level and 1,888 feet above sea level for the seasonal high conditions. And under the seasonal low, we see a range of 877 to 1,887. So here we have our 2018 seasonal high contours for the alluvial aquifer. And as you can see, the highest elevations occur in the eastern part of the basin, near that 1,860 contour line. And the lowest elevations occur in the western part of the basin along that 900 contour along the Santa Clara River. Generally speaking, the flow in the alluvial aquifer is to the west and toward the Santa Clara River. And here we have some generalized flow lines that show which direction groundwater is flowing. Our next example, here's the seasonal low conditions for 2018 in the alluvial aquifer. And these are very similar to what we see under seasonal highs. Minimal variation, only a slight shift where groundwater elevations are just slightly lower than what we saw in the seasonal high conditions. And the direction of flow is almost identical to what we see under the seasonal high conditions. I want to point out in the southern part of the basin, the South Fork area where you don't see any contours. That isn't suggesting there's a lack of water there, that's suggesting there's a lack of data. So under the seasonal low conditions, we didn't have as much water level data to develop these contours, so we weren't able to present contours for those areas. But for the areas where data was available in the lower portions of the South Fork basin, the water levels fell between this 1020 contour and this 1100 contour. Okay. Now, moving on to the Saugus Formation, which underlies the alluvial aquifer, we see deeper groundwater elevations and deeper in depth to water. So under the seasonal high conditions, those vary between 50 and 185 feet. And under the seasonal low conditions, those are between 50 and 217 feet, which translate into the groundwater elevations you can see below. And in the picture I have to the right here, this is just an example of someone taking a depth to groundwater measurement at a well. So first we have our seasonal high conditions. We don't have as much coverage in the Saugus aquifer as we do the alluvial for reasons Anthony had discussed. There aren't as many wells because parts of the Saugus aquifer don't produce as much groundwater. But for what these contours tell us, the direction of flow is generally to the west. So we have these same flow lines that shows which direction groundwater is flowing. And it's mostly flowing west with some data indicating there is flow to the east in the western part of the basin. Next, we have our seasonal low condition contours. We see a little more variation between our seasonal high and seasonal low contours, but the general flow directions remain the same. Okay, now that we've covered our groundwater elevation contours, which provide us a snapshot of conditions, the current conditions for 2018, we're going to look at the hydrographs. And this looks at the groundwater elevation at a specific well, and how does this change over time? And do we see any seasonal variation? Is there any long-term trends due to dry and wet periods? And it'll also indicate the historic highs and historic lows at a specific well. So for the alluvial aquifer, I look at two wells. I look at a well in the eastern part of the alluvium and also a well in the western part of the alluvium. So do we see any differences in trends, and what do we see on a seasonal basis? So here we have those results dating back to the late 1950s. And what this tells us is that there's been a cycle of rising and declining groundwater levels, especially in the eastern part of the basin. These wells don't indicate that there's any chronic decline of groundwater elevation. We see in the east that you have rapid increases in groundwater elevation during wet periods, and then over 5 to 10 year periods, you see a gradual decline due to dry conditions. And what this also tells us is that we don't see very much seasonal variation between these. We see long-term trends, that we see changes in groundwater elevation. And for our western well, we see a completely different, not completely different trend, but we see very steady groundwater elevations with no cycle of rapid increase and then gradual decline. This is possibly due to what Anthony had discussed in his presentation. In the western part of the alluvium, you have saugus water that is recharging the alluvial aquifer. So that's a possible explanation for what we see here. And something to keep in mind about the current conditions and why groundwater elevations may be lower than what they have been historically is that we're in an exceptionally dry period. Going back to the mid-2000s, there has been well below average precipitation, and that has resulted in another one of these cycles where we see a continual decline in groundwater elevations, and we haven't yet seen that rapid increase as we have in the past. Okay, so now let's look at the hydrographs for the saugus aquifer. And again, I have two examples. This is in the center part of the basin, and in the southern part of the basin, we don't have anything in the north as it's not a water-bearing part of the basin, and there's not as much data there. But here we see a little bit different response than what we saw in the alluvial aquifer. We do see patterns of declining and rising groundwater elevations, but on a little different time scale. We saw 5 to 10 year periods of increasing and declining groundwater elevations in the alluvium, but here we're seeing rising and lowering water levels over roughly 25-year periods. And historically, we don't see long-term decline. Again, we're in another cycle where you see lower groundwater elevations, and we have those exceptionally dry conditions dating back to the mid-2000s. So in these hydrographs, you see we may be near historic lows, but again, under normal conditions where we have another wet year, those are likely to recover. And the key difference between the results of these saugus hydrographs and what we saw in the alluvium is that you see a lot of seasonal variation. You see jumping between seasonal high and seasonal low conditions, which you didn't see in the alluvial aquifer. Okay, so now moving on to groundwater storage. Groundwater storage is a requirement of SIGMA where the amount of change in the volume of water from year to year will need to be calculated. This is important because if we understand how much storage changes in the basin from year to year, it will help with future planning. Knowing the amount will help us understand how does climate and groundwater extraction affect the available supplies. So the change in groundwater storage is going to be determined using the groundwater flow model that is being developed for the water budget section of the GSP. We're not presenting any results here today. And we determine that on a year-to-year basis from what DWR defines as their water budget or their water year, which occurs from October through September. So to calculate the difference of storage from 2017 to 2018, you're going to look at the difference in the total volume of water from 2017 September through 2018 in September. And the change in storage is going to be the difference between the inflows and the outflows. And Anthony had discussed some of those, but some examples of inflows into the aquifer would be precipitation, losing streams. That's where you have surface water flowing to the groundwater system. Groundwater inflows, that's going to be interactions between the alluvium and the saugus aquifer. And then artificial recharge. There's projects that you can do to increase the amount of recharge to an aquifer. Outflows include groundwater extraction, gaining streams where you have the groundwater discharging to the surface water, and then groundwater outflows. Our next topic is seawater intrusion. This is where you have seawater in the subsurface actually interfere with the groundwater supplies that are used by a basin. This is not applicable to the East Subbasin, but it's one of the required elements of SGMA, and it needs to be identified. And in the GSP, this is going to be stated that this does not apply to the East Subbasin plan. Okay. Our next topic is subsidence. Subsidence is the gradual lowering of the land surface due to the withdrawal of fluids from the subsurface. And this can be withdrawal of water or withdrawal of oil. And as you remove fluids from the subsurface, those pore spaces between the sediments will start to compact, and that can result in the lowering of the land surface. The picture I have here on the right is from the Central Valley in the San Joaquin River Valley. And you can see over the past 30 years, you have significant subsidence of 6+ feet. And this is an important aspect to consider because a lot of subsidence can result to damage to infrastructure, roads, and bridges. But also, if you have excess subsidence, you can actually lose groundwater storage because of the compaction of those fine-grained sediments. So we have 2 continuous GPS monitoring stations in the East Subbasin, and these date back to the early 2000s. And these 2 stations indicate that there are not any long-term subsidence in the East Subbasin. The scale on these graphs are the intervals on these are 5/100 of a foot. And you see minor changes every year, but not enough to notice or cause any damage to infrastructure or cause any potential loss to groundwater storage. In our next topic, we're getting into groundwater quality. And this is another requirement of SGMA. And the importance of understanding groundwater quality is we are able to quantify the different constituents that may be in our groundwater, all of the dissolved substances that are naturally occurring or maybe the result of contamination. So the general groundwater quality section of this GSP is going to focus on 4 main constituents, and that includes total dissolved solids, or TDS, chloride, nitrate, and sulfate. And we're going to present some concentration graphs for each of those for each of the aquifers and how they've changed over time. But we're also going to discuss our contaminants of concern. And there are 4 primary contaminants of concern in the subbasin, which includes perchlorate, volatile organic compounds, or VOCs, and there are 2 specifically, PCE and TCE. And then we're also going to discuss PFOS, which is an emerging contaminant of concern. So first, total dissolved solids. This is all of the salts, metals, or any organic materials that may be dissolved in water, primarily made up of things such as calcium and magnesium, potassium, sodium. And this is a general way to understand the salinity of your water as well, as it's a lot of different salts and anions and cations. The EPA has a secondary maximum contaminant level, and this is a recommendation of what the EPA believes is appropriate for drinking water. And it's based primarily on aesthetics. What is the color of the water? What is the taste, and does it have any odor? So the EPA recommends 500 parts per million. And so we're going to look at our water levels as compared to these standards. Locally, the Regional Water Quality Control Board has set a water quality objective of between 700 and 1,000 parts per million. And those vary based upon those different tributary areas we discussed. So there are numbers for the Saugus Formation, but across the alluvial aquifer, there are different standards for TDS that are between these 2 values. So first, we're going to look at some alluvial wells and their TDS concentration in the center part of the basin here. And we have this red line represents the water quality objective of 700 milligrams per liter, which also is the same as parts per million. And we don't see any consistent trends. We see groundwater concentrations near the water quality objective, in which they stated these objectives and these secondary MCLs are recommendations, and this is the raw groundwater concentration we're talking. There hasn't been any treatment at this point. And so next we have our Saugus wells. and these are primarily in the central and southern part of the basin. And here we see similar trends. We have groundwater concentrations near and around the water quality objective. Some more stable than others, and some showing some increase in recent years. Our next constituent we're going to look at is chloride, and this is a naturally occurring in groundwater. The sediments that make up the aquifer, when they come in contact with water, they can dissolve and result in chloride concentrations in the water. But the concentration of chloride can also increase as a result of human activity, urban runoff, and then discharge from recycled water. The negative impact of high concentrations of chloride include salty tasting water. The EPA recommends a secondary MCL of 250 parts per million, and then the regional board recommends between 100 and 250 based on local conditions. So we're going to look at some wells in the eastern part of the basin for the alluvium. And here we see the chloride concentrations dating back to mostly the early 90s. And our concentrations here are showing a slight increase, but overall groundwater quality concentrations are below the water quality objective. Okay, next are Saugus wells. And here we see no increase at all with chloride concentrations that have historically been below the water quality objective. Okay. Our next constituent of interest is nitrate. And this can result as from agricultural activities or septic tanks and land fertilizers. And unlike TDS and chloride, nitrate has a primary maximum contaminant level of 45 parts per million. And the reason being is that high consumption of water in high concentrations can have negative health effects. One specifically is blue baby syndrome, which can affect the blood's ability to transport oxygen throughout the body. So the MCL set by the EPA is 45 parts per million, and the regional board also has a water quality objective of 45 parts per million. And here we're going to look at some wells in the eastern part of the basin. And historically, these wells have all been below the water quality objective. And our Saugus wells in the central and southern part of the basin. And again, all well below the water quality objective, so no health threats based upon the current groundwater concentrations of nitrate. Next, we're going to look at sulfate. This is also naturally occurring in groundwater, specifically in the Saugus formation. Because of the sediments that make up the Saugus, you see higher concentrations of sulfate. You also can get increased sulfate from industrial waste. And this is a secondary MCL. There's no significant health risks, but consumption of water with high concentrations can have a laxative effect. And that's when you're in well in excess of 250 parts per million. The regional board recommends a water quality objective between 150 and 350 parts per million. So here are alluvial wells in the center part of the basin. And historically, concentrations for sulfate have been below or around the water quality objective. And next are Saugus wells. And the regional board hasn't set any water quality objectives, but you can see that the concentrations here are slightly higher than what we saw in the alluvial aquifer. And then finally, groundwater quality. We're going to discuss the contaminants of concern. And the first contaminant is perchlorate, and this is commonly used in rockets, propellants for rockets and missiles and fireworks. And consumption of groundwater in high concentrations can result in issues with the thyroid gland. This has been an issue in the basin, but there are currently cleanup programs underway that are treating wells that have been impacted by perchlorate. And the Department of Drinking Water recommends an MCL of 6 parts per billion. Another contaminant of concern in the basin are the volatile organic compounds, which includes TCE and PCE. The MCL for each of these are 5 parts per billion. And these were commonly used for remove grease from metal parts, but also the PCE was used in dry cleaning processes. Consumption of these over long periods of time can result in cancer when you consume water with high concentrations for extended periods. But the detections in the basin have been very low, and none have been above the MCL of 5 parts per billion. And then lastly, we have PFOS. And this is a large group of substances that was used a lot in manufacturing dating back to the 1950s, used a lot in firefighting foams and nonstick cookware, stain-resistant carpets and furniture. And the reasons it was so commonly used was that its ability to repel oils, waters, and grease. But the 2 most common forms of PFOS are PFOA and PFOS. These are not currently regulated substances, but they are emerging substances of concern. EPA has established recommendations of not using water in excess of 70 parts per trillion. But DEW has recommended response levels of 40 parts per trillion for PFOS, and then PFOA, they recommend 10 parts per trillion. And we're still learning, or the EPA is still understanding what the impact or what the effect PFOS can have on health, but right now it's considered a possible carcinogen. So here we have the results for the contaminants of concern. We have the max concentrations detected in a single well, along with what the MCL or the response level is. And again, that response level is a non-regulatory standard. And you can see there have been some wells that have been affected by these contaminants, but for each of these wells, action has been taken, whether it be the well is destroyed, or there's some treatment in place, or the wells are currently taken out of service. So with that, I will open it up for questions.
Takes me like 4 clicks. So I'm trying to, and I've got a couple more questions that just came in, so I want to make sure that those are included in my notes. So let's start with a question from, going back. A question from Stacy Fortner. So she asked, or she had a constituent ask why there's so much chlorine in our water and why does everyone need water softener. So there's a question about hardness in the groundwater, and I was wondering if you could address that. And if we need to bring Jeff in, we can. Jeff?
I think Andrew is muted.
Say it's probably due to technology.
There you go.
You know,
Andrew, I think you were muted.
Oh, okay. It's a function of the geology and the sediments that make it up. Chloride is, you know, it's an anion and a component of salt. And as Tony discussed, this is sulfates. This is a, you know, an area that was underwater, so there's going to be a lot of seawater influence here. And that makes up the sediments and why you might see higher concentrations of chloride.
This is Dan. Clarification. No, she was asking about chlorine that relates to the treatment. You know, I mentioned it really needs to talk to agency staff about that. It's not really pertinent to this discussion. So it was about chlorine, not chloride.
Oh, I'm sorry. I misunderstood.
Yeah. Very specifically chlorine in the, why is there so much chlorine in our water? So,
Well, I think Dan's correct that the agency would be better to answer that question, but it is the commonly used disinfectant. The agency can speak to the concentrations that are in different parts of the distribution system.
and
Yeah, it's for
Steve,
health.
did you want to, Steve, could you step in and just kind of maybe address that a little bit?
Sure. Sure. Can you hear me?
Yes, we can.
Yeah, this is Steve Cole, Assistant General Manager for Santa Clarita Valley Water Agency. Yeah, chlorine is a requirement by health standards to make sure that there's a disinfection residual in the drinking water. And so depending where you're at throughout the water system, you can have different levels of chlorine residual as the chlorine dissipates over time throughout the distribution system. So we'd be happy to talk in more depth to the customer here. And I think, I don't know if Kathy's done it yet, but we can get you the number of our water quality staff, and they'd be happy to walk you through the specifics of chlorine residual management for the agency.
Kathy actually did provide the number, so that's also listed in the chat. All right, the next question is from Dan Moran. Is the increase in groundwater during 1992 period due to a 100-year storm? To which Dan replied, March Miracle, but I'd love to hear a little bit more about where that increase might have come from.
So could you repeat the years again?
Absolutely. Is the increase in groundwater during the 1992 period due to the 100-year storm?
I would defer to Will or our senior principal hydrogeologist or Jeff on that question.
Yeah, I would say during that period of time, I wouldn't say it was just a singular storm, but we're coming out of the late 80s, early 90s drought, and where you see recoveries in groundwater levels, they're often associated with an increase in recharge due to a wetter, period of time.
I would agree with that. In fact, I think it was 1991 when that really wet period happened, which could have resulted in higher water levels beginning then.
All right, Maria Gusite had a question of, wouldn't change in storage be somewhat theoretical since things are not continuously monitored, stream flow, surface infiltration, etc.? And it seems like it's a combination of estimates. Is that correct? As opposed to municipal pumping, which we specifically measure.
Yeah, that's going to be, based upon our understanding of the aquifer in the areas where we have groundwater elevation. So it's going to be generally an estimate that the numerical model develops for the areas that, we know the aquifer well, and there's going to be some assumptions for areas where we may not understand the aquifer as well, but Tony can speak to that on the areas where we understand what's going on.
I wouldn't say it's theoretical. I would say it is based on the historical data that's been collected, and then you use your understanding of aquifer conditions and groundwater levels in various parts of the basin to develop estimates of change in groundwater storage. So I wouldn't necessarily classify that as being theoretical.
All right, does that answer your question, Maria?
Yeah, it does.
Okay.
I mean, all of it is some kind of estimate because we only have data for certain parts, like you said. But I just found it interesting that is one of the indicators, as opposed to things that are more quantitatively measured. But that's fine.
Well,
Yeah, Maria, it's very closely tied to changes in water levels. It's a very consistent gauge, and in fact, I'm not quite sure why they have change in storage as a sustainability indicator when we have chronic lowering of water levels.
The
we have to
water
answer
levels,
that question.
Yeah, the water levels make a lot more sense.
Yeah.
The reason why there's two different sustainability indicators is when you have areas where you have what's called a confined aquifer, where water is under pressure, the change in groundwater levels in those sorts of aquifers don't really result in a whole lot of change in actual physical volumes of storage. And that's where the groundwater levels are most represented as a sustainability indicator. Change in storage is a greater indicator of overdraft in more unconfined or water table type aquifers where the water levels are under gravity pressure. And so that's why there's those two. But getting back to the change in storage calculations, one of the exercises in developing the GSP and under Sigma is to identify areas where historically you don't have very good data collection, and those are called data gaps. And part of the requirements of Sigma is to identify those data gaps and to propose monitoring to where you can address those data gaps so you can get a much better understanding of what the basin's conditions are going forward in time.
Great.
We're going to talk a lot more about change in storage when we get into the water budget discussion later on in another workshop.
Perfect. So Kathy asked, are each pair of wells shown in the graphs representative of data for all the wells?
They're generally representative. The well on the east that I showed for in the alluvial aquifer, we see that similar pattern, and a lot of wells kind of show that same cyclic period, that same cycle. There are other wells that we discuss in the tech memo and will be included in the GSP that may show a slightly different trend or potentially slightly increasing or decreasing ground elevation. But generally, I'd say it's representative, and the same is true for the Saugus wells.
Great. Kathy, that makes sense? You following?
Yes, thank you.
Perfect. Diane asked, do we have an estimate of the available water in the Saugus formation?
That'll be answered in the water budget workshop in the water budget section of the GSP.
All right.
Great. So it's still in debate, in flux?
Is the question?
Well, I would add to this, there's a question about total storage in the Saugus, which I think Dan was commenting on, and that's not the same as available storage or how much storage you can capturable storage. Essentially, that's one of the things we'll be getting at in the sustainability plan is how much groundwater and storage is there that can be captured by wells, and how much should we capture that's available. So there's a distinction there between available and total.
Thank you.
Thank you for the clarification. Lynn asked, are there only 2 gauges adequate to measure subsidence all over the basin? Are only 2 gauges adequate, or do we need more than 2 gauges?
I was only able to identify 2 continuous GPS stations. Whether that's called a data gap, that'll need further consideration. But given that in the 2 locations where we have data and we see no long-term subsidence, at this point I would say it's probably not a data gap or would need any further data collection. But there are other methods you can use to measure subsidence using wells as proxies. But that'll be addressed as the GSP is developed more.
And I would add to that, what Andrew was mentioned about using wells in particular, you can look at both the geology in certain areas of the basin to get a sense of whether you feel like the geology exhibits the characteristics that would be prone to subsidence. And you can also look at groundwater level trends over time to get a sense if you have chronic lowering of groundwater levels that would result in subsidence, assuming you have the geologic conditions that would be suitable for such a thing.
Does that get to the heart of what you're asking, Lynn? Okay, I'm gonna
I would
go
add, there's one more point that
Yeah.
I would add, if Lynn's still listening, is, you know, if we were to allow groundwater levels to drop significantly below where we observe them now in the future, you know, we'd have to be more concerned about subsidence and whether or not it's likely to occur. If we maintain groundwater levels within their historic range, or we don't go below the historically measured levels, then chances are we're not going to be making a subsidence issue. So just to throw that out there. So a lot of this depends on where we choose to set these minimum thresholds for water level. How far down do we let the water levels go?
This is Dan Mosnata real quick. I remember past discussions with Bill Scalmanini and Richard Slade, where they were explaining to me that the nature of the geology is such that subsidence isn't really an issue here in the valley as opposed to, say, up in the center, as compared to the Central Valley. That was basically what they were explaining to me. But again, like you said, Jeff, as long as we're within the operating yield of the aquifer.
Yeah, it's the collapse of the water-bearing clays and thick sequences of clays that you see in the Central Valley that is the biggest problem causing subsidence. And we don't have those, you know, substantially thick clay layers here in this basin.
Great. And then moving on to the next question that Lynn had, the hydrologists have actually, it's Maria's question. Isn't it correct to say it's regulated because we have to provide notice to customers for PFAS, PFOA, not established limit yet, because you do not have to take action? Just checking in on that.
Can you repeat that question? That seems like that may be.
Absolutely. It was a PFAS, PFOA question, and it's specific to what we were talking about a little bit earlier. And isn't it correct to say that it's regulated because we have to provide notice to customers versus, and then like not an established limit yet, but we have to take action?
Well, I think that's probably best responded by.
This is Dirk. Maria's correct. What we have is a response level at this time. We do not have a minimum contaminant level that EPA or DEW would issue. If we were to deliver water in excess of that response level, the state would require us to notify our customers that we were doing that. And in an abundance of caution, what we have done is make a determination to take those wells offline until such time as we can install treatment that would assure that we're not delivering water in excess of those response levels.
And then Lynn had a question that said, but we did have some nitrate problems in the alluvial wells in the Pony League field. I believe it was septic system contamination. Is that reflective of what you guys were talking about, or can you speak to that?
So in the wells that we've looked at, they're generally below, and currently they're below the 45 parts per billion, but I'm not familiar with this specific issue.
Jeff, are you familiar with it? Do you know what she's talking about?
I don't know that specific example, but I do know that the data we're looking at is basically production well information. And so it's possible that there are places in the basin where there are localized contamination issues, for example, from septic tanks, that could be a problem. We just don't have it documented.
And I would add to that, what we're looking at is publicly available data, groundwater quality data. So but of course we're always interested if there's additional data out there to incorporate and develop a better understanding of groundwater quality conditions in the basin. We would welcome seeing it.
You may want to check with Keith Abercrombie, who used to be at Blunter Water, another in the service area. I think it's-
All right, is there any other input or feedback, questions? I see no other hands raised, and I see nothing in the chat window. Are we going to actually end on time / 6 minutes early? Is everyone excited? All right, so just before we leave, thank you so much to our presenters. I'd like to share this resource with you guys to make sure that you, if you could stop sharing, Andrew, I'm gonna share my screen for a minute. And I want to introduce you to this resources page. For additional information about what we've been talking about today, if you go to scvgsa.org/groundwater sustainability workshop or click public workshops right here in the menu, there's also a big button on the homepage. You can find the presentations that we just listened to, in addition to the technical memos as they currently stand, with additional information, including informational PDFs, which will load very slowly because I'm on screen. So informational PDFs and videos about these topics, if you'd like to continue. And then there's a survey at the very bottom, which gets into how we did in terms of educating you on this particular topic. These will change every single time for each workshop, and allow you to add any information that you'd like us to have in the report. So all of this will be recorded and then reported back to both the committee, the board, and then included in the plan. Does anybody have any final questions? All right. Have a lovely evening, everyone. And this is our first workshop. See you soon.